In the mid-1950s, the United States, the most powerful nation on Earth, was gripped by a profound and growing anxiety. Its entire national defense strategy, a doctrine known as massive retaliation, rested on a foundation that was visibly cracking. The strategic deterrent, a vast fleet of strategic air command bombers and a nascent force of land-based missiles, was vulnerable. By 1957, this vulnerability was no longer a theoretical problem. It was an immediate, existential threat. This strategic nightmare, born from a sudden technological leap by its adversary, propelled one of the most audacious and consequential engineering endeavors of the 20th century. It was a quest to solve a problem that most of the military establishment deemed physically impossible: how to hide an intercontinental ballistic missile in the one place the enemy could never find it: the deep, unforgiving, and mobile abyss of the ocean. This is not simply the story of a new weapon. It is the story of a doctrinal war fought inside the Pentagon, a bitter rivalry between the Air Force and the Navy for the future of America's nuclear soul. It is the story of three seemingly impossible engineering hurdles: a revolutionary new fuel, a perfect navigation system, and a method for launching a 30-ton rocket from underwater without killing the crew. And ultimately, it is the story of how a small group of engineers, working against a crash deadline, solved all three problems at once. In doing so, they not only created the Polaris missile system, they engineered the very foundation of modern nuclear deterrence: a stable, terrifying peace built on the concept of mutually assured destruction. The strategic landscape of the Cold War was irrevocably altered in 1957. On August 21st, the Soviet Union successfully flight-tested the SS-6 Sapwood, the world's first true intercontinental ballistic missile. Just weeks later, on October 4th, they used the same R-7 rocket type to hurl a 184-pound polished sphere into orbit. That sphere, Sputnik, became a dramatic symbol of Soviet technological prowess, beeping its way across the night sky and sending a shockwave of inferiority and fear across the American public. But as terrifying as Sputnik was to the public, the ICBM test just weeks earlier had far more ominous and immediate security implications for the Pentagon. These events catalyzed a profound anxiety within the U.S. government, giving rise to the missile gap, a widespread public misperception that the Soviets had a dangerous and growing lead in long-range missiles. This perception, though later proven to be a myth, had fateful consequences. It ratcheted tensions to near public panic levels and fueled a political firestorm. This public panic was given classified validation by the 1957 Gaither Report. This top-secret review, commissioned by President Eisenhower to assess the vulnerability of the nation, delivered a horrifying conclusion. The entire Strategic Air Command, SAC, bomber fleet, the heart and soul of America's deterrent, was vulnerable to surprise attack. This was the tyranny of fixed locations. The entire U.S. nuclear arsenal, every SAC bomber base, every nascent missile silo, every command bunker was a list of known, static, targetable coordinates on a map. The Soviet Union, with its new ICBMs, now knew precisely where to aim. The strategic nightmare was not just the existence of the Soviet bomb, but the crippling vulnerability of the U.S. launch sites. A Soviet first strike, known in military doctrine as a counterforce strategy, would be designed to wipe out America's ability to retaliate before President Eisenhower could even pick up the phone. This geographic vulnerability defined the perfect solution. The only true deterrent was a weapon that was not on the map. The only answer was an invisible, mobile launch platform that the Soviets could never find,
never target, and never destroy in a first strike. The only answer was a submarine. But this solution presented its own set of seemingly impossible engineering challenges. The concept of sea-basing a missile was not new. The Navy had experimented for years with weapons like the Regulus, a nuclear-armed cruise missile, but this was a clumsy, tactical weapon. The submarine had to surface, deploy the missile on its deck, and launch it like an airplane, a process that left the sub exposed, slow, and vulnerable. To create a true strategic deterrent, the obvious answer seemed to be simply placing the Army and Air Force's new land-based ICBMs onto a submarine. This, however, was deemed a suicide mission. Early long-range rockets used either cryogenic propellants like the Atlas or Jupiter, kerosene plus LOX, or later, storable hypergolic propellants like the Titan II, Aerozine 50, and nitrogen tetroxide, each posing different, deadly hazards aboard a boat. First, cryogenic propellants. Liquid oxygen, LOX, must be kept near -183 degrees Celsius, -297 degrees Fahrenheit, making it impractical to store aboard a submarine for long periods. You cannot store liquid oxygen in a missile's fuel tank. It would instantly boil off, causing catastrophic ice formation on the missile's skin and venting explosive oxygen gas into the submarine. This required a significant operational delay, as the rocket would have to be painstakingly fueled before launch. Second, hypergolic propellants. The Titan missile and the Army's Jupiter IRB used storable liquid fuels, but these were, if anything, more dangerous in a confined space. These were hypergolic propellants like hydrazine and nitrogen tetroxide. Corate. Hypergolic fuels are highly volatile, dangerous to handle, toxic, reactive, and corrosive. They ignite instantly and violently on contact with each other. A single pinhole leak in a pipe or a valve inside a submerged submarine would be a non-survivable event, poisoning the crew or causing a catastrophic explosion. The U.S. Navy, which had initially been a reluctant partner in the Army's liquid-fueled Jupiter missile program, quickly and forcefully concluded that its propellants were an unacceptable hazard during at-sea operations. The engineering was a dead end. In December 1956, the Navy officially abandoned the Jupiter program. The fuel problem had to be solved. Without a fuel that was as powerful as a liquid, but as safe and stable as a solid, the entire sea-basing concept was dead. But this formidable engineering problem was only the first shot in a bureaucratic war that would define the next 50 years of nuclear strategy. The quest for a submarine-launched missile was not just an engineering challenge, it was a bureaucratic war for the future of U.S. nuclear strategy. Inside the Pentagon, the Navy, led by the formidable Chief of Naval Operations, Admiral Arleigh Burke, was championing a new and controversial doctrine of finite deterrence, also called minimum deterrence. Burke and the Navy argued that the only thing needed to deter the Soviets was a small, invulnerable force. This force wouldn't need to strike hundreds of targets. It only needed to guarantee, beyond any shadow of a doubt, that it could survive a first strike and deliver a devastating attack in response. This second strike capability alone was enough to ensure the new, terrifyingly stable doctrine of mutually assured destruction, MAD. This new idea directly contradicted the dominant, established doctrine of the U.S. Air Force. The Air Force, led by the powerful Strategic Air Command, was built on a doctrine of massive retaliation, a counterforce strategy. This required a massive arsenal of thousands of bombers and ICBMs, not to target cities, but to target hundreds of Soviet military installations, airfields, and missile silos in a winnable nuclear war. The Air Force's most powerful counterargument was that the Navy's finite deterrence was a technological fantasy. They argued that the engineering problems were in fact impossible. It's a pipe dream. You can't build a solid fuel rocket powerful enough to be an ICBM. You can't navigate a submerged submarine with enough precision to hit a target 1,000 miles away. And you certainly can't ignite a 30-ton rocket from inside a submarine without killing the entire crew. Thus, the engineers at Lockheed, Aerojet, and the MIT Instrumentation Laboratory were not just building a missile, they were building the proof of concept for the Navy's entire strategic doctrine. Solving these three formidable problems was the only way for Admiral Burke to win the argument inside the Pentagon and secure the Navy's future. The engineering triumph was, at its heart, a bureaucratic one.
The Polaris program, officially created in December 1956 and given the highest national priority, became a crash 3-year effort. It became one of the greatest engineering gambles of the Cold War, to build a missile small, safe, and rugged enough to live inside a submarine, and accurate enough to strike a continent from the deep. Its success and the future of the Navy's strategic relevance depended entirely on a triumvirate of engineering teams solving those three formidable problems in parallel. The failure of even one would mean the failure of all. The program was catalyzed by a single radical concept presented at the 1956 Project Nobska study, a high-level conference on submarine warfare. There, physicist Edward Teller argued that nuclear warhead design was advancing so rapidly that a 1-megaton warhead could soon be shrunk to a much-reduced weight. This revelation profoundly affected the course of the program. It meant the Navy no longer needed to build a massive submarine to house the enormous liquid-fueled Jupiter missile. It could now build a smaller, new design around a much smaller, lighter missile. This created the first formidable problem: to invent a solid fuel propellant that was, for the first time, powerful enough to be an ICBM, yet stable enough to be safely stored and handled for months inside a submerged submarine. Existing solid fuel was safe but weak, suitable only for small rockets. The volatile, powerful liquid fuels of the Atlas and Titan were a suicide mission. The engineers needed a third way. The breakthrough was an ammonium perchlorate composite propellant, APCC. Powdered aluminum, a potent high-energy fuel, in a polymer binder. The oxidizer was ammonium perchlorate, and the motors used a polyurethane-type binder. Castable, energetic, and storable. This new fuel was incredibly energetic, perfectly stable for storage, and critically, it could be cast into any shape. The impossible fuel was now a reality. The contract to develop and produce the motors was awarded to Aerojet General. The second challenge was industrial. Manufacturing processes for such large rocket motors were groundbreaking in the 1950s. First, the motor casing. It had to be both lightweight and strong enough to contain the immense pressure and 6,600 Fahrenheit heat of the new propellant. Instead of steel, engineers at Aerojet built the motor for the advanced A-3 missile from a fiberglass filament-wound case, a revolutionary use of lightweight composite materials. Second, the propellant itself. A critical problem with solid rockets is that, unlike liquid engines, they cannot be throttled or shut down. Once lit, they burn all the way after ignition. The thrust is a direct function of the surface area that is burning. The Polaris engineers solved this with a brilliant, simple design. The propellant was not cast as a solid block, which would burn only from the bottom up. It was cast with a large hollow core running down the center, shaped in a 6-pointed star configuration. This star grain was a work of engineering genius. It created a massive internal surface area. When ignited, the entire inner surface of the star burned at once, producing the enormous, stable thrust needed for an ICBM. As the star's points burned outward, the surface area changed in a precisely calculated way, managing the thrust curve for the entire flight. This geometry was, in effect, a throttle, designed into a solid, unthrottleable block of fuel. The solid fuel motor solved the problem of power, but power is useless without accuracy. This was the second formidable problem: navigation. To hit a 1-mile-wide target from 1,200 miles away, the submarine commander must know his exact position on Earth at the moment of launch. But the submarine is submerged, moving silently for months at a time, and GPS does not exist. How do you aim a rifle when you are blindfolded, in the dark, on a moving platform? The solution came from one of the great, unheralded geniuses of the 20th century, Dr. Charles "Doc" Draper and his MIT instrumentation laboratory. Draper's monumental effort was to create what he called the ideal arrangement, a self-contained black box that could navigate for extended periods without dependence or information from the outside world.
The device was the ship's Inertial Navigation System, SINS. This was not a simple compass or radio. The SINS was a complex, gimbaled, gyro-stabilized platform. This platform was a physical marvel, a housing isolated from the movements of the ship. On this stable platform, a set of ultra-precise gyroscopes sensed any rotation, pitch, roll, and yaw. A set of equally precise accelerometers sensed any linear movement, changes in velocity. The SINS was, in essence, a mechanical brain performing continuous dead reckoning. A navigation computer integrated these millions of tiny, continuous measurements of motion. If it sensed an acceleration eastward for 10 seconds, it knew it had moved X feet east. It literally kept track of every twist, turn, and surge of the submarine 24 hours a day. Draper's inertial navigation, SINS, was a mechanical genius, a self-contained black box that dead-reckoned position with astonishing 1950s precision. Drift accumulates, but accuracy was enough for Polaris targeting and its 1 nautical mile circular error probability, or CEP. This SINS was the mother guidance system. Its primary function was to provide the missile's own internal guidance system with its initial conditions for the ballistic equation. A missile in its tube is blind and dumb. Before launch, it must know 3 things: where am I right now, where is the target, and which way is up and which way is north. The SINS mother system provided these answers. It talked to the missile's own guidance system, aligning its gyros and telling it, you are currently at X latitude, Y longitude. North is this way, up is this way, and we are already moving at 4 knots. The fire control computer instantly used this data to solve the ballistic equations and train the missile to the proper bearing. Only then was the missile ready to be launched, its own internal brain now fully aware and able to guide the rest of the 1,200-mile flight. The engineers now had a powerful, storable motor and a brilliant, all-knowing brain, but they faced a final, seemingly insurmountable hurdle: the launch. Igniting a multi-ton rocket motor inside a sealed, pressurized submarine was considered too dangerous. Corey, the immediate back pressure, the 6,000-degree heat, and the massive volume of toxic exhaust gases would instantly kill the crew, destroy the aft end of the submarine, and send it plunging to the bottom. It was, quite simply, physically impossible. The missile had to be ejected from the submarine and propelled to the surface before its powerful first-stage motor ignited, its 6,000-degree flame hitting open air instead of the submarine's hull. This system, this underwater cannon, had to evolve. The later Polaris A-3 missile was significantly heavier. The compressed gas gunpowder was no longer powerful enough to eject it. Corey, so the engineers replaced it. The heavier later missiles, A-3 and beyond, required hot gas or steam ejectors that flashed water into high-pressure steam to shove the heavier missile free before ignition. This pivot to a steam-powered cannon was a necessary reinvention, driven by the success of the motor and warhead engineers. The engineers at Aerojet had built a more powerful engine, so the engineers at Westinghouse had to build a more powerful cannon. The impossible triumvirate of engineering solutions was complete.
The three impossible engineering solutions: the powerful solid motor, the all-knowing inertial brain, and the revolutionary cold-launch cannon were a pure engineering triumph. But in 1959, they existed only in separate laboratories, on test stands, and on blueprints. The final act of the Polaris program, and its greatest programmatic achievement, was to forge these three disparate technologies into a single, mobile weapons system. Aerojet, motors; MIT Draper, SINS; Westinghouse, launch systems; and electric boat, hulls, and installation forged the system together, and to do it at a crash speed that defied all industrial precedent. To meet the urgent timeline created by the missile gap panic, the Navy, championed by Admiral Hyman Rickover and Admiral Arleigh Burke, made an ingenious and highly unorthodox decision. Instead of waiting years for a new class of submarine to be designed from scratch around the 16 missile tubes, they took one that was already being built. At the General Dynamics Electric Boat Shipyard in Groton, Connecticut, workers were building the USS Scorpion, SSN 589, a new skipjack-class fast-attack submarine. In a move of incredible industrial improvisation, the Navy ordered the shipyard to perform a daring factory-level hull modification. Rather than a brand-new design, Electric Boat inserted a 130-foot missile compartment into an existing skipjack-type hull under construction. This cut-and-weld approach was the single most important programmatic decision of the entire effort. The modified submarine was renamed the USS George Washington, SSBN 598. The keel for the original Scorpion was laid in November 1958. The George Washington was launched just 7 months later, in June 1959, and commissioned in December 1959. This audacious engineering shortcut saved the Polaris program at least 2 years. In just 2 years, the Navy had gone from an unacceptable hazard concept to a fully commissioned, nuclear-powered ICBM-carrying submarine. This speed, this physical manifestation of national will, was the true answer to the panic of Sputnik. This bridge of disparate technologies, Aerojet's solid fuel motor, Draper's inertial SINS, Westinghouse's cold launch cannon, and Electric Boat's hull, all converged for the final test. On 20 July 1960, the George Washington proved it. Submerged off Cape Canaveral, the USS George Washington, with the program head Admiral William F. Rayborn on board as an observer, prepared to conduct the first-ever submerged launch of a ballistic missile. Declassified footage captures the sequence. The cold launch system worked. A massive burst of compressed gas forced the missile out of its launch tube like a cannonball. Image of declassified footage of Polaris A-1 launch. The Polaris A-1 missile, with a mass of roughly 30,000 pounds, broached the surface in a spectacular plume of spray, stabilized, and, a safe distance from the sub, its first-stage solid motor ignited. The rocket streaked 1,100 miles down the Atlantic Missile Test Range. The submarine's commander, James Osborne, sent President Eisenhower a historic message. The telegraphed words were, "Polaris, from out of the deep to target. Perfect." About 2 hours later, they launched a second missile. It also hit its target. This test was the singular moment the pure engineering triumph was validated. The word perfect was not just pride.
It was the final, irrefutable confirmation that all three impossible engineering tracks had converged at the same time in the same place. Aerojet's fuel, Draper's navigation, Westinghouse's launch, and Electric Boat's hull had all worked as one integrated system. On 15 November 1960, the George Washington departed for the first 60-day operational deterrent patrol, carrying a full complement of 16 armed Polaris missiles. The impossible weapon was now on station.
The legacy of this triumph was the 41 for Freedom. This fleet of 41 nuclear-powered ballistic missile submarines, built at a furious, unprecedented pace between 1959 and 1967, changed the world. These boomers, as they became known, were the perfect bridge, combining the absolute stealth of the submarine with the strategic continent-spanning power of the ICBM. This new weapon system, born from a crash engineering effort, definitively solved the strategic nightmare from Act 1. That nightmare was the tyranny of fixed locations, the vulnerability of every bomber base and missile silo that gave the enemy a tempting first strike target. The silent patrols didn't make the fleet invincible. They made a survivable, assured second strike a strategic reality, dramatically lowering the odds of a successful first strike. This assured second strike capability was the final piece of the strategic puzzle. It guaranteed, beyond any doubt, that even if the United States was destroyed in a devastating surprise attack, a devastating response would come from the cold ocean depths. This capability, this certainty of retaliation, removed all logic from a first strike. Why attack if you cannot destroy the enemy's ability to strike back? The 41 for Freedom were the physical, engineered guarantors of mutually assured destruction, MAD. By creating an assured second strike, this pure engineering triumph made a winnable nuclear war an impossibility. The engineers at Lockheed, Aerojet, and MIT, in solving their three impossible problems, had not just built a weapon, they had created the most stable, if terrifying, piece of the entire Cold War. The system would not remain static. The engineering evolution from the first A-1 missile to the A-3, which was operational just 4 years later, demonstrates the incredible pace of the program. More range, better accuracy, and multiple warheads, all engineered and deployed in less than 4 years. The Polaris program was not just one single invention. It was the creation of a continuous, rolling wave of technological superiority that would define the strategic balance of power for a generation.